Hi, welcome to this lecture on collections. Here's an outline for this lecture. We'll talk about what are called collections or data structures, and these are basically mechanisms for working with collections of data. So far we've been talking about how you manipulate individual data values, but in this lecture we'll focus on collections of values. Okay, and the different collections that we're going to consider are lists, tuples, sets, and dictionaries. And then we will talk about a concept called comprehension, which will allow you to work with these collections in a fairly convenient way. And then finally we'll discuss some advanced looping techniques. So let's get started. What is a collection? A collection is a way of organizing data that you wish to process in your computer program. Okay? Now a collection is also called a data structure. Our first example of a collection is going to be the list, which is also known as an array. So a list is basically a collection that stores a sequence of references to objects. Okay? Now the easiest way to create a list in Python is to place comma-separated values between matched square brackets. Okay. Now before we look at an example, keep in mind that any list that you create in Python is basically an object of the built-in type list. So list is a built-in type, and it's a built-in sequence type, meaning it stores a sequence of references to objects. Okay. So any list that you create in your program is an object of this type list. So here are some examples of lists in Python. In the first line here, what we are doing is creating a list called suits that contains the values which are these strings: clubs, diamonds, hearts, and spades. And notice how we create this list. We simply separate these values, these four strings, by commas inside of matched square brackets. Okay? So that's the syntax for creating a list in Python. So suits is now a list containing four string objects. In this next example, what we are doing is creating a list called X, where the values are 0.3, 0.6, and 0.1. So notice again, the values are separated by commas inside of matched square brackets. So here X is a list of 3 floats. Okay? So these are a couple of examples that show you how to create a list in Python. Now, after you create a list, you can refer to any individual object within the list by specifying the name of the list followed by an integer index within square brackets. Okay, so for example, if you want to get hold of diamonds from this particular list suits, you would say suits indexed by the number 1. Why is it 1 and not 2? Well, it's because lists are 0 based. So the first index here is 0, the second one is 1, and then this is 2, and this is 3. So keep in mind that the indices start at 0. What if you want to get hold of this particular item from the list X? Well, you would say X indexed by 2. Okay? So suits at 1 corresponds to the string diamonds, and X at 2 corresponds to the floating point number 0.1. Right? So that's how you access an element within a list. Here is another example where that's shown. So let's say we have two lists of floats, X and Y, and let's say that they have lengths given by some variable n. Okay? Now what this code is showing you is how you calculate the dot product of the numbers in X. So what is a dot product? Well, let's look at a quick example that shows you how you compute a dot product. So let's say X is the list 1, 2, 3, and let's say Y is the list 2, 3, and 4. So what is the value of n here? Well, n is 3 because both X and Y have 3 elements each. So what is the dot product of these two lists? Well, it is very simple. You multiply these two guys together, which is 2, and add to that the product of these two guys, which is 6, and add to that the product of these two fellows, which is 12. So what do you get? You get 20. So the dot product of X and Y is 20. Okay? So that's how you compute the dot product of two lists. And this code does exactly that. you initialize total to 0, which is going to store the result or the dot product, and then I simply goes from 0 all the way up to n minus 1. Okay, and what we say is the new value of total is the old value of total plus the ith element of x times the ith element of y. Okay, so for example, when I is 0, we are multiplying 1 and 2 and storing that in total. And then when I is 1, we are multiplying 2 and 3 and adding that result to the previous value of total and storing the new value back in total, and so on and so on. So at the end of the for loop, total is going to contain the dot product of x and y. Okay, and here is a trace of this code when x is this particular list of 3 elements and y is this particular list of 3 elements. So n is 3 here. Okay, so let's walk through this trace. So total is initialized to 0 initially, that's this line here. And then I is 0. That's the very first value of I in this for loop. So what are we doing here? We are multiplying x at 0 with y at 0, which is 1 times 4, because x at 0 is 1, y at 0 is 1. So 1 times 4 is 4. And that result is added to the current value of total. So total goes from 0 to 4. Okay? And then in the next iteration, I becomes 1. So now you're looking at these two elements and multiplying them. So 5 times 2 is 10, so that's what you see there. And that's added to the current value of total. So total now becomes 14. Okay? And then I becomes 2, which is the last value of I. And now we are looking at these two elements of x and y, 3 and 6. We multiply them to get 18. That's added to the current value of total. So the new value for total is 32, and that is the dot product. Okay, so it's a nice little example that shows how you work with lists. Now, remember that we refer to the first element of an n element list A as A at 0, the second element as A at 1, and so on. And the last element, the nth element of the list, is referred to as A at n minus 1. Okay, so again, keep in mind that the indices go from 0. For an n element list, the indices go from 0, 1, 2, and so on, all the way up to n minus 1. Now, at runtime, we can get the length of a list, or we can compute the length of a list A using the built-in function len. All right, so if you have some list A, and if you want to know how many elements A has, you can simply say length of A, and that will return the number of elements in A. And you can use this operator plus equals to add an element to a list. Okay, so let's say you have some list and you want to throw in a new element at the very end. How would you do it? You would use this operator plus equals. And here is an example that illustrates that. So let's say you want to create a list A with n floats where each element is initialized to 0. Okay, so for example, if n is 3, you want to create a list that has the 3 values set to 0. Okay, so you want to end up with such a list. So what's the code that will do that? Well, here's the code. So A starts out as an empty list. So this line here is an empty list with no elements in it. And then I goes from 0 all the way up to n minus 1. So if n is 3, then I is going to take on the values 0, 1, and 2. Because range of 3 is the progression 0, 1, 2. So in the first iteration, I is 0. So what do we do in that case? What we do is we use this operator plus equals to append this particular element to the list A. Right? So this is basically the syntax for appending this element to the list A. And remember not to forget the square brackets. Okay, because if you just say 0.0, it's meaningless because you're then appending a number to a list. That's no good. So what we need here is to append this particular value at the end of the list A. All right, so these square brackets are extremely important. Okay, that's part of the syntax. So that's how you append a value to a list. Okay? A plus equals, in square brackets you put the value. All right, so A starts out empty. And So let's trace this. So that's A, that's I, and then when I is 0, we are appending this value to the list. So now A becomes a one element list that contains 0.0. And then in the next iteration, I is going to become 1. And now you append one more 0 to the list. So A is now a two element list whose elements are 0 and 0. And then finally I becomes 2. And you do this once more. You append 0.0 to that list. And you have a three element list, okay, where all values are initialized to 0.0. Okay, so that's how you create a list from scratch, right? Starting from nothing. Now, lists are extremely fundamental data structures in that they have a direct correspondence with memory, right? So what does that mean? It means that when you create an array such as A, in that example there, then A is basically a pointer to a memory location. So A really contains a memory address such as 522, for example. Okay, and this we know from our discussion before, that everything in Python is an object and the name of an object is essentially a memory address. So is A. Right? So A is a memory address, but since A is an array, what do you find when you go to that particular memory location? So if you go to 522, what you will find is first the length of the array itself. So if A is an 8 element list, then the value here at the memory address 522 is going to be 8. And then what follows are the 8 values of the list. So A at 0 is going to be at 523, A at 1 is going to be at 524, A at 2 is going to be at 525, and so on. And A at 7, the last element or the 8th element, is going to be at 530. Okay. So notice that the values of the list are stored continuously in memory. Okay. And that's what makes accessing an element of an array extremely efficient. So if you know that you want, let's say, like the 5th element of a list, you can simply get it out by saying A at 5, and because of this kind of a storage mechanism, you are able to get that element out extremely efficiently. Okay? And that's what we mean when we say that there is a direct correspondence between a list and memory. Okay? Now, lists are mutable objects because we can change their values. So here is an example that illustrates that. So what this code does is it takes a list A, right, and it simply reverses it. So for example, if A is 1, 2, 3, 4, and 5, if it's a 5-element list, then once this code is done, then A is completely reversed. So A becomes 5, 4, 3, 2, and 1. Okay? And this code is able to reverse this list in place, meaning it doesn't create a new list in order to reverse the given list. Okay? So that's important. So that's what makes this code fairly efficient. So let's walk through the code. So what we're doing first is getting the length of that list using the built-in function length. So for this particular list, n is going to be 5. Right? And then I goes from 0 all the way up to n integer division 2. So for example, if n is 5, such as in this example, this number here is going to be just 2 because it's 5 integer division 2. So in that case, I is simply going to take on the values 0 and 1. Alright? So I is 0 and 1 if n is 5. Okay, and then what we do in the body of the for statement is simply exchange the values at the index I with the value at the index n minus 1 minus I. Okay, so, and this is the standard swapping idiom. You store the value at I in A in the variable temp, and then you assign A at I to be the value of A at n minus 1 minus I, and then the value of A at n minus 1 minus I is simply whatever temp is, which is the old value of A at I. Okay? So what we are doing is, in the first iteration, we are swapping these two guys. So that is when I equals 0. And then in the second iteration, we swap these two guys, which is when I equals 1. And once you do that, you're done with the for loop, and then A takes on the values exactly this, because when 1 and 5 are swapped, 5 comes here, 1 goes there. When 2 and 4 are swapped, 2 goes there and 4 comes here. Okay? So that's what we do. We basically, in each iteration, swap the value at I with the value at n minus 1 minus I. And here's a trace of this code. So we have this array A, which is 1, 2, 3, 4, 5. N is 5. And the possible values of I, as we just discussed, are 0 and 1. So in the first iteration, what we're doing is swapping A at 0 with A at 4. So 5 comes here, 1 goes there, and then in the next iteration, when I is 1, we are swapping the values at 1 and 5 minus 1, which is 4, minus 1, which is 3. So we are swapping the values in A at 1 and 3, which is these two guys. Okay? So 4 comes here and 2 goes there. And we are done with the for loop, and notice that now A is the reverse of the input. All right? So a very nice piece of code that quite efficiently reverses a given array. Now, one of the most fundamental operations that you perform on a list is to simply walk over or iterate over all its elements. Okay? And there are a couple of ways of doing that. And here's an example that shows how you compute the average of a list of floats using a for loop. And here, since you want to calculate the average of all the elements in a list, you have to look at all the elements. You have to iterate over all its elements. And this is a particular way of doing it. Okay, so how is this calculating the average of a list A of floats? Well, we initialize total to 0, so that's going to store the sum of all the values in the list. And then I simply goes from 0 all the way up to the length of A minus 1. Okay? Remember, length of A gets the number of elements in A, and then I simply goes from 0 all the way up to the number of elements in the array A minus 1. Okay? And then what we do is we grab the ith value in the array A and simply add it to total. Okay? So once the for loop is done, total is going to be the sum of all the values in A. And at the end, we calculate the average as the sum, the total, divided by the number of elements in A. That's the standard formula for the average of a list of numbers. Okay? So let's trace this code now. So let's say our input, the list A, contains these values 1, 2, and 3. Right? So how does this code compute the average? Well, total starts at 0. And then what are the possible values for I? Well, length of A in this case is 3, right? So length of A is 3. When that is the case, what is this range? A range of 3. Well, it's the progression 0, 1, and 2. So I takes on the values 0, 1, and 2. Okay? So when I is 0, what we do is we get the 0th value of I and simply add it to total. So total now becomes 1.0. And then in the next iteration, I becomes 1. So you add the first value of the array, meaning the value at A at 1, to total. So you add 2 to 1 to get 3. Right? And then in the last iteration, I takes on the value 2. So you add A at 2, which is 3, to total to get 6. Okay? So once the for loop is done, total has the value 6. And then in this line, we simply calculate average as total divided by the length of A, which is 3, to get 2 as the average. Okay? So this code correctly computes the average of the numbers in a list. Now notice that here we are iterating over this list A using indices. So this style of iterating over a list is called iterating using index, because I here serves as an index, okay? And A at I is the value, right? So keep that in mind. I is an index and A at I is the value. Okay. Now there is another way to iterate over a list. Okay, and that's what we're going to talk about next. So here, this code does exactly the same computation, meaning it calculates the average of a given list A. But here we are iterating by value. So iterating by value. Okay, and here's how it works. So we initialize total to 0 just like before, but notice now the for loop says for v in A. So there is no range or anything like that. Okay, so we have a variable v for value. You can call it whatever you want, but v is a good name here because we are iterating by value, and then we simply put the list right there. Okay, and then the rest of the code is fairly straightforward. So inside of the for loop, we say take that value, the current value that we are looking at in A, and add it to total. Right? And once the for loop is done, we calculate the average exactly the way we did in the previous slide, right? As total divided by the length of A. But notice here that in each iteration, v is a value from the list. Okay, it's not an index, and hence this style of iteration is called iteration by value. And for this particular example, where we calculate the average of a list of numbers, we really don't need the indices of each element in that list. Okay, so we just need to look at the values, which is what we are doing here. Right? You typically need access to the index when you're modifying a list. But if you're really not modifying the list, if you only need a read-only access to the list, then this style of iteration is more natural. I mean, it's recommended that you use this style of iteration. Okay. Right. So here is a trace of this code for the list A equals 1, 2, 3. Okay. So total is initialized to 0, and then in the first iteration, v is 1. Okay. So v is basically the first value in that list. And what do we do with that value? Well, we simply add it to the current value of total, so total is now 1.0, and then v is the next value in the list, which is 2.0. What do we do with it? Add it to the current value of total, so total is now 3, and then finally v is the third value in the list, which is 3.0, add it to the current value of total to get 6. The loop is done, and then finally we simply divide total, which is 6, by the length of the list A, which is 3, to get the average as 2.0. Okay, so the code correctly computes the average of the given list, but notice that it did so by simply looking at the values directly, right? We didn't make use of the indices of the elements here. So these are basically two styles of iterating over a list, one using index, the other one using values. Now Python has several built-in functions that take lists as arguments, meaning there are several built-in functions that operate on lists. So here are some examples. Given a list A, you can calculate the number of elements in A by saying length of A. So this is something that we talked about. And then you can use the built-in function sum to compute the sum of the elements in A, right? And then you can get the smallest element in A using the built-in function min. You can get the largest element in A using the built-in function max. Okay, these are just a few functions, built-in functions that operate on lists. There are other functions as well. Now notice that since we have these two functions, we can rewrite the code for calculating the average of the values in a list in one line. So we can simply say average equals sum of A, which is the total of all the elements in A, divided by the number of elements in A, which can be obtained by saying length of A. So this one line code has the same effect as this code here or the code from the previous slide. Okay, you can do it in one line. Now, if you want to write out the values of a list, you can do that in one line by calling either stdio.write or stdio.writeln, giving it an argument which is a list. For example, you can say stdio.write a list A or stdio.writeln a list A. Right? But if you want a finer control over how you write the elements out, then these functions are not that useful, but what you can do is simply do a for statement, right? You can use a for statement to write each element of a list individually and the way you want, right? So using a for statement gives you more control in how you write the elements, right? Okay, now there is something called aliasing, which refers to the situation where two variables refer to the same object. Okay, so let me give you an example of that. So here in this example, X is the list containing the elements 0.3, 0.6 and 0.1, and then we say Y equals X. So in memory what you have is something like this. X is a pointer to the list 0.3, 0.6 and 0.1, and then since we say Y equals X, Y is also pointing to what X was pointing to, right? And then if you go about saying X at 1 equals 0.99, so if you so when you say X at 1, you're talking about this particular element, you're changing that from 0.6 to 0.99. Okay, now since Y also points to the same list, then if you go about accessing Y at 1, you get 0.99. Okay, so that's what aliasing is all about. So when you say something like Y equals X, Y is pointing to what X was pointing to, right? So keep that in mind. So if you want to make a copy of a list, this is not what you want to do. So you don't want to say Y equals X and assume that Y is going to be a new copy of X such that when you modify X, Y doesn't change. So if you want a genuine copy of X and not an alias to X, then this code is what you want to use. Okay, so this will get you a completely fresh copy of the list X. So let's see how it works. It's fairly straightforward. You start Y as an empty list, so that's this line here, and then you iterate over the values of the list X by value. Okay, so for each value in the list X, you simply append that value. So remember the syntax for appending with the square bracket. So you simply append the value V to the list Y. So once the for loop is done, Y is exactly a copy of X, but it's a fresh copy. Okay, so in this case, X is pointing to some list in memory, such as 1, 2, 3. And then Y, once this code is done, is pointing to a new list, which has the same elements as X. Okay, but it's a completely new list. It's a genuine copy of X. So now if you go about changing, let's say this guy to 4, Y doesn't change. Y still remains at 1, 2, 3. Okay? So if you want a fresh copy of a list, this is the code that you want to use. But there is also an alternate syntax for that, and that's what we're going to talk about next. So Python allows something called slicing that you can use to slice a segment of a list. So if you have a list A, you can get a segment from it that starts at I and ends at J, where J is not inclusive, by using this syntax. So when you say A square brackets I colon J, you get a new list out of it which contains elements starting at I and ending just before J, meaning it contains the elements A at I plus 1, and so on all the way up to A at J minus 1. So the element at J is not included. Okay, so keep that in mind. And now I and J are optional, meaning you don't have to specify them. So if you simply say A colon, I defaults to 0 and J defaults to, let me write this here, J defaults to the length of A. Okay, so if you don't specify I and J, then what this results in is a copy of the entire list, right? Because it is as if you have 0 for the value of I and length of A for the value of J. And what does that mean? It means I want a copy of A that contains all the elements in A. Okay, so in other words, this syntax A square brackets and just a colon makes a fresh copy of A, and this is equivalent to this code here. So all that we have written here can simply be written as Y equals X colon colon. right? So no value for I, no value for j. So this has the same effect as these 3 lines of code. It gets you a completely fresh copy of x. Okay. Now, the authors of the IPP text that we use in the course, they have provided a module called stdarray. So just like stdio and so on, this stdarray is a module from the authors of our text that defines the, several functions that you can use to work with lists. And here I'm showing you the API for just a couple of functions from that library, and there are other functions as well. Okay. So what does this first function do? Well, the first function lets you create a one-dimensional list of size n whose values are all initialized to this value. Okay, and stdarray.create2d creates a two-dimensional list. We'll talk about two-dimensional list later on, that has m rows and n columns, and all the values are initialized to this value here. Okay, so let me give you a quick example of create 1D. So for example, if you want to create a list of 7 booleans where everything is initialized to false, you would simply say stdarray dot create 1D with 7 as the first argument, because we want 7 booleans and we want everything initialized to false, so the second argument would be false. Okay, so when you do this, this results in an array whose 0th element is false, first element is false, and so on all the way up to the 6th element, which is also false. Okay, so this is index 0, index 1, and so on all the way up to index 6. So that's how this function works. It lets you create a one-dimensional list of size n where all the values are initialized to what you specify as the second argument. Now keep in mind that a string is nothing but a list of characters. Okay, so you can think of a string as a list, and what it means is you can manipulate a string just like a list, right? So you can use some of the built-in functions that operate on list to also operate on a string. So you could, for example, say len of some string to get its length, right? So if you say len of the string Bob, this is going to result in 3, right? And you can also do slicing on strings. So if you say something like, so let's say s is the string Bob, you could say s 1 and 3, 1:3. So you can slice a string. So in this case, I is 1, j is 3. So what is this going to be? This is going to result in a string whose elements are O and B. Okay? So it's the string OB. So strings can be manipulated just like lists, because a string is nothing but a list of characters. Now, this entity that we are quite familiar with, sys.argv, which stores all the command line arguments, we know exactly what it is now. It's basically a list object, and it is a list that contains string objects. And what are these strings? These strings are the command line arguments. Okay, so sys.argv is basically a list of strings where the strings are all the command line arguments. And since it's a list, you know how to manipulate it. You can use the built-in functions and things like that. You can slice this list and so on and so forth. Okay. So for example, if you want to figure out the number of command line arguments, you could simply say len of sys.argv. If you want to slice it, you can use this slicing syntax. All right? Okay. So let's look at a concrete example where we create and manipulate lists. Okay. And this code is going to be some code that processes playing cards. Right? So let's first come up with a representation for suits and ranks, right? In a standard deck of 52 cards. So we can create a list called suits. Okay? We are using all caps because this is we're treating it as a constant. Okay? So suits is simply a list that contains the strings, clubs, diamonds, hearts, and spades. And then we define another list called ranks, again all caps because we want to treat it as a constant, and this contains all these strings, okay, 2, 3, 4, 5, 6 and so on, all the way up to ace. Okay, so 13 elements here. So we have the suits and we have the ranks. So we basically have a representation for these two guys, suits and ranks. Now let's say we want to write a random card name. Right? So we have a deck, let's say, standard deck, and we want to pick out a card at random and write it out. What's the Python code that would simulate that? Now, this is how you would do it. You would first get a random rank by saying rank in lowercase, so that's a variable, equals random.randrange from 0 through the length of ranks. What is the length of ranks? It is 13. So rand range is going to return a random integer between 0 and 13, where 13 is not inclusive. Okay, so it's going to be a random number between 0 and 12. Okay, and then we say suit is a random integer between 0 and the length of suits. What was that? Well, that is 4. So here suit is going to be a random number between 0 and 3. So this is between 0 and 3, and this is a random number between 0 and 12. Okay? And then what we do is we simply write this particular string to the output. But what is this part here? Ranks at rank is basically indexing this array ranks by this number. Okay? When you do that, you're going to get a random element from this list, and then suit at suit is basically indexing this array using the suit value, okay, which is going to return a random element from this particular array. Okay? So this code has the effect of printing a random card. So this card, for example, might come out as let's say ace of diamonds. Okay. All right. Now, what if you want to write some Python code to create an entire deck of 52 cards? Well, here's how you would do it. We would represent a deck as a list. So we start with an empty list, so deck is empty. And then we have two for loops that iterate these two lists by value. So for rank in ranks, so for each rank in this list ranks, and for suit in suits, so for a particular value of rank, we go through all the values in suits. Okay? And then what we do is we build the string called card as the rank value, which is going to be an element from here, concatenated with of plus the suit value, which is going to be an element from this list. Okay? And once we have that, we simply append it. So notice this is the syntax for appending to this particular list deck. Right? So we are appending a string to that list. So once these loops are done, deck is going to have 52 strings in it, where each string represents a particular card. Right? Now let's say we have our deck and we want to shuffle it, because that's something that you typically do with playing cards, right? So how do we shuffle it? Well, so here's the code that does that. We first get the length of the deck, so that's n, and n is going to be 52. Okay, and then what we do is I goes from 0 all the way up to n minus 1, which is 52 minus which is 52 minus 1, that is 51. So I is going to take on values 0, 1, 2, and so on, all the way up to 51. Okay, and then we say we obtain a random number r between I and n. So in the first iteration, I is 0 and n is 52. So we get a random number between 0 and 52. Okay? And then this piece of code, if you remember, is the standard code that you use to exchange two values. But in the first iteration, what are we exchanging? We are exchanging the card at 0 because I is 0. So we are exchanging the card at 0 with a card that's at a random location between 0 and 51. Okay, so that's what we do in the first iteration. So we have all these cards, 0, 1, 2, and so on, all the way up to 51. Now when I is 0, we are simply exchanging this guy here with some random card that is ahead of it. So let's say it is exchanged with some card here. Okay? And then I becomes 1, so I is now pointing to this fellow here. But then when we get the random number, it is between 1 and 52. All right, so that's going to be a random number from 1 all the way up to 51. So let's say that falls somewhere there. So you exchange these two cards, right? And then I becomes 2, you exchange it with some random card. I becomes 3, you exchange it with some random card, and so on and so on. And then once the for loop is done, the entire deck is shuffled. Okay, so it's a very nice piece of code that shuffles a list, shuffles the element in a list. In this case, it shuffles the deck of 52 cards. Okay, so now let's look at a Python program called sample.py that takes two integers m and n as command line arguments, and what it writes to the terminal is a random sample of m integers from the range 0 through n minus 1, right, where m and n are command line arguments. And notice that there are no duplicates in the output. Okay, so for example, if m is set to 5 and n is set to 10, then the output is going to be 5 numbers without duplicates that are drawn from the range 0, 1, 2, and so on, all the way up to 9. Okay, an example of 5 such numbers might be like 7, 3, 1, 4, and 2. Okay. So let's see how the program implements this. So we import all these modules. We import random because we're going to be drawing elements at random. We import stdarray because we want to be creating one-dimensional arrays. And then we import our usual modules, sys and stdio. Then in the first two lines, we get the two command line arguments, m and n, as integers. And then we set up an array called perm, a one-dimensional array called perm for permutation that has size n and everything is initialized to 0. Okay, so if n is, let's say, 10, then after this line of code, perm is going to be 0, 0, 0, and so on, all the way up to the index 9, right? So this is index 0, index 1, index 2, and so on, all the way up to index 9. And then in this for loop, what we say is perm at I equals I, where I goes from 0 all the way up to n minus 1. All right. So for this particular example, where n is 10, once this for loop is done, perm at 0 is going to be 0, perm at 1 is going to be 1, perm at 2 is going to be 2, and so on, and perm at 9 is going to be 9. So that's what you get after this for loop is executed. Okay. So we set the ith element of perm to simply be I, where I goes from 0 all the way up to n minus 1. Okay? Now this is what we call a genuine permutation of size 10. Okay, and then comes a piece of code that we saw in the previous slide. So what are we doing here? I goes from 0 all the way up to m minus 1. So if m is 5, then I goes from 0, 1, 2, and so on, all the way up to 4. Okay, and what is this code? Well, from the previous slide, you should recognize this code as the code that shuffles the m values in the list perm. Okay, and so convince yourself that this is exactly that code which would have the effect of shuffling the first m elements of the list perm. Okay, so what we have done is, so once this for loop is done, the first m elements of this list is going to be, so m is going to be shuffled. All right. So for this particular example, where m was 5, the first 5 numbers are going to be put in random order or shuffled. Okay. And then this piece of code simply prints the first m values of the shuffled values, the m shuffled values, right? Because that's what we are interested in, right? We are interested in a random sample of m integers. Okay. So we simply shuffle the first m elements of perm, and then in this for loop we print the first m elements of perm. So I goes from 0 all the way up to m minus 1, and we simply ask for the ith element as a string and concatenate it to a space and write that out without a new line character. And once the for loop is done, we write a new line character. Okay. So let's look at some input and output. So let's say we run sample.py with m equals 6 and n equals 16. So we want a random sample of 6 elements where each element is from the range 0 through 15. And here is what we get. Okay. Notice that it is a random sample of 6 elements, no duplicates, and these values are from the range 0 through 15. Here's another example, a random sample of 10 elements where each element is from the range 0 through 99. Right? And then finally here we are asking for a random sample of 20 elements from 20 elements. So here m and n have the same value, 20 and 20. So we get a random sample of 20 elements, no duplicates, right? And each element is from the range 0 through 19. And here, since m equals n, we basically get each value from the range exactly once. Okay, and we get all of those values 0 through 19. And you can check that out. Okay, so that's a nice program where we work with lists. Here is another program where we put lists to use. So this program is called couponcollector.py. It takes an integer n as a command line argument, and n is going to represent number of unique coupons that are out there. Okay, and let's say an individual is into collecting coupons, and we want to figure out how many coupons you have to collect in total until you have one of each of the unique coupons, right? So that's what this program tries to address. It takes n as a command line argument where n represents the number of unique coupons, and it writes to standard output the number of coupons that you need to collect before you obtain one of each of n types. Okay? So let's see how it's done. We import these modules, random, stdarray, stdio, and sys. We get the command line argument n as an integer, and then we initialize two variables, count to 0 and collected count to 0. So count is going to represent the total number of coupons, and collected count is going to represent the number of unique coupons. Right? And then comes the very important part. We create a one-dimensional array called isCollected, where of size n, where everything is set to false. Okay. Now this is the array or list that we're going to use to remember which of the unique coupons has been collected so far. Okay. And initially we are saying that we haven't collected anything, so we set every element to false. Okay. So let's take n to be 5. So there are 5 unique coupons. Label 0, 1, 2, 3, and 4. Okay, so isCollected is going to be this array, and everything is initialized to false to begin with, meaning you have not collected any of these coupons so far. Okay, so that's the interpretation of this array isCollected. It remembers which coupons you have collected so far. And then comes the while loop, where we go about collecting coupons, and we do so until collected count is strictly less than n. Because what does it mean for this Boolean expression to be true? It means that we haven't collected all the unique coupons yet. There is still something out there that we don't have in our possession. Okay, and it is exactly when collected count equals n that we know that we have collected all we have all the n types. of coupons. Okay, but until then we need to collect more. Okay, so what do we do in the while loop? Well, we collect a coupon. So that's a call to random.rand range from the interval 0 through n. Okay, so this is going to give me a value between 0 and 4, for example, when n is 5. Okay, so that's my random coupon. So value is a random coupon, and since I just collected a coupon, I increment the total number of coupons by 1. So that's this line here. And then what we do is very interesting. We check if this value is something that we have already collected or not. So we go to the array is collected, we index it by value, okay, which is this random coupon, and we check if it is not true. So not true. So what does it mean for this value to be not true or false? It means that we have not collected this particular coupon so far. It's the first time we are seeing this coupon. So in that case, we increment collected count by 1, okay, because this is the first time we are seeing this coupon, and now we remember the fact that this coupon was just collected. So if value, for example, came out to be 3, what we do is we go to the third index, which is this particular fellow, and change it to now true, meaning I've collected this coupon, okay, and so on. And at some point, it's very clear that collected count is going to be precisely n, in which case we are out of the while loop and we end up printing the total number of cards that we had to collect. Okay? So that's how the program works. Let's look at some input and output. If we run it with n equals 1000, the program says we need to collect about 6000 cards until we have one of the 1000 types. Meaning until we have each of the 1000 types. And then here we run it again with n equals 1000, and it comes back with a different number than before, and that is to be expected because this is a random process after all. So here it says you have to collect about 8000 cards until you have one each of the 1000 types. And then here we run it with n equals 1,000,000. The program comes back with this number. Okay. All right, so that's the coupon collector problem, and here, I mean, this program, again, you know, it's a nice example that illustrates how you work with arrays. Okay, and it illustrates this important idea of how you use a Boolean array such as this one to remember things. Okay? This is something that you do a lot in programming, so make sure you understand how this works. Okay? Our next program is a very interesting one. It's called prime_sieve, and what it does is it takes a command line argument n as an integer, and it writes to standard output the number of primes that are less than or equal to n. Alright, so if n is 10, the program is going to write output of 4 because there are 4 primes that are less than or equal to 10. Why is that? What are the primes less than or equal to 10? Well, it is 2, 3, 5, and 7. So you have exactly 4 primes less than or equal to 10. Okay, so that's what the program does. It prints the number of primes less than or equal to n, where n is received as a command line argument. So before we look at the code, let's see how this is, how the algorithm works. So this algorithm is an ancient one. It is due to this gentleman called Eratosthenes, right? So this algorithm is also called sieve of Eratosthenes. It's an ancient algorithm. It's at least some 2000 years old. So what is the algorithm? How does it work? Well, what we do is, if n, for example, is 10, then we create an array of size 11, right? And that's what is shown here. So we have an array called is prime that is of size 11, and here I'm simply showing you the values from the index 2 all the way up to 10. Index 0 and 1 we don't care about. All right. And this is going to be a Boolean array where initially all the elements are set to true. Okay, so the element at 2 is set to true, element at 3 is set to true, and so on, and the element 10 is set to true. What is the interpretation of this array? We are saying that to begin with, every number, 2 is a prime, 3 is a prime, 4 is a prime, and so on, and 10 is a prime. That's what we're saying. Okay? We don't care about 0 and 1 because we know that 0 and 1 are not primes. Okay? So initially we are saying all the numbers from 2 through 10 are primes, which is clearly wrong, but that will eventually be fixed by the algorithm, right? So let's see how that is done. Okay, so initially everything is true, and then what we do is I takes on the value 2, and we simply consult the array and see what the corresponding value is. So at is prime of 2, what do we have? We have true, meaning 2 is a prime number. So in that case, what we do is we mark its multiples as being non-primes or false. Okay, so what is the next multiple of 2? Well, it's 4, and 4 we mark as false. Okay, since it's a multiple of 2, it cannot possibly a prime. So 4 is now marked as not a prime. What's the next multiple of 2? It's 6, mark it as not prime. What is the next one? 8, mark it as not prime. The next one is 10, mark it as not prime, and we are done scanning the array. Okay? And then I takes on the value 3. Here again the same thing, go to is prime of 3, which is true. Now you simply mark its multiples as being not primes. So what's the next multiple? Well, it's 6. Mark it as not prime, but it was already marked as not prime. And then go to its next multiple, which is 9. Mark it as being not prime, and then we are done scanning the array. Now the next value is 4. Consult the array, but is prime of 4 is not a prime, it's a false, right? It was marked false here. So we don't do anything in this case, simply look at the next value for I. What is prime of 5? Well, it is true. Now you go about marking its multiples as being not primes. So its next multiple is 10, which was already marked as not prime. Okay? Then I becomes 6. Well, if you go to I at 6, it is false, so it's not a prime, we don't do anything. I becomes 7. You go to I at 7, it is true. You mark its multiples as being not primes, but there is nothing because the array is just 10 elements. So we are done right away. And then when I becomes 8, is prime of 8 is false, so there is nothing to do. I becomes 9, is prime of 9 is false. We are done with the algorithm. And now notice look at the values in the array is prime. Okay? So how do we now figure out the number of primes less than or equal to 10? Well, it's very simple. Simply scan through this array is prime and count the number of true elements. So you have 1, 2, 3, and 4 true elements. And that is basically the number of primes less than or equal to 10. Alright, so that's the algorithm. So now let's see how this algorithm is implemented as Python code. Okay, so we import our usual modules, and then we get the first command line argument n as an integer, and then we set up this array is prime with size n plus 1. So when n is 10, it is set up with a size of 11, okay, where the indices go from 0 through 10. I have suppressed the indices 0 and 1 because those are not prime, but what is shown are the indices 2 through 10. Okay. Now notice all the elements are initialized to true to begin with. So initially we are saying every I is a prime number from 2 all the way up to n, which is 10 in this case. So we're saying initially everything is prime to begin with. Okay? And then what we do is, this is where we actually implement the sieve algorithm. So I goes from 2 all the way up to n minus 1, and we simply check if I is a prime number or not by consulting the array is prime. So if is prime of I is true, we know that I is a prime number. So in that case, what we do in this for loop is we check off its multiples as being not primes. So j now goes from 2 all the way up to n integer division I. Okay. So j goes from 2 all the way up to n integer division I, and we simply check the multiples of I as being not primes. Okay, so initially I was 2, and for this particular example here, what is n? It is 10. 10 integer division 2 is what? This whole thing is 5. So 5 plus 1 is 6. So j takes on the values 2, 3, 4, and 5. Okay, so j first takes on the value 2. So 2 times 2, which is 4, we say is prime of 4 is false. So that's how this element became false. And then j becomes 3. So 2 times 3 now is 6. That's how this element becomes false. And then j becomes 4. So 2 times 4 is 8. That's how this becomes false. And then finally j takes on the value 5. 2 times 5 is 10. That's how this element becomes false. And then we are done with the j loop. I now becomes 3, and we look at this guy here. Okay? So that's basically the sieve of Eratosthenes' algorithm. And then all that we have to do is count the number of true elements left in the array. So we initialize count to 0. I goes from 2 all the way up to n, and we simply check if is prime of I is true or not. If it is, we increment count by 1. Okay, and then once the for loop is done, we simply print count, which is the number of primes less than or equal to n. So here is some input and output. If we run the program with n equals 25, the program comes back with 9 because there are 9 primes less than or equal to 25. If we run it with n equals 100, the program comes back with 25 because there are 25 primes less than or equal to 100, and so on and so on. Okay? It's a very nice program that shows how you can use a one-dimensional list of booleans here to figure out the number of primes less than or equal to n. Okay, so far we have talked about one-dimensional lists, but in many applications, a natural way of storing information is using a table of numbers which are organized in a rectangular table, okay, or a matrix. And we typically refer to the rows and columns in the table. Okay? So what we are saying here is, in many applications, it's more natural to represent or store your information as a matrix or a table that has rows and columns in it. How do we create a two-dimensional list or a table in Python? The easiest way to create such a list is to place comma-separated one-dimensional lists between matched square brackets. So as you can see, it is the extension of the same syntax as for one-dimensional lists. So here is an example. So let's say you want to create a two-dimensional list in Python that represents this matrix that has 2 rows. So m, the number of rows, equals 2. So that's a row count, rows. And n is 3. And that's columns. So how do we represent this table or matrix in Python? Well, here it is. So A is a list, and it is a list that contains 2 one-dimensional lists separated by commas and in matched square brackets. Okay. Now what does this list correspond to? That's the first row in the table or the matrix, and this list here corresponds to the second row. Okay. That's it. So that's how you create a two-dimensional list in Python. Now, how does Python represent a two-dimensional list that has m rows and n columns? Well, in memory, it is going to be represented as follows. This is very important to keep in mind. So if you have an m-dimensional, m by n dimensional a list in Python, Python simply stores it as a one-dimensional list that contains m items in it, index 0, 1, 2, and so on, all the way up to m minus 1. And each element here is a one-dimensional list, okay, that has n elements in it, 0, 1, 2, and so on, all the way up to n minus 1. Okay? And so, and the last row here is a one-dimensional list that contains n elements. Okay. Now, since Python uses this kind of a representation, if you want to figure out the number of rows of a two-dimensional list A, you can simply say length of A. Okay, so that's what I'm talking about here. So you can get the number of rows of a matrix or a two-dimensional list by saying m equals length of A. What about the number of columns? Well, assuming A is non-ragged, meaning it has the same number of columns in each row, if that is the case, you can simply ask for the length of this particular list for the number of columns, right? But if A is this list, how do I get hold of this list? It is simply A at 0. So this list can be referred to as A at 0. So A at 0 is simply this list. So if you get the length of that, that's going to be the number of columns of the matrix A, right? Again, assuming that A is non-ragged, meaning each row has exactly the same number of columns. So if A is non-ragged, you can get its number of rows using that idea, and you can get the number of columns using that idea. Okay, so keep that in mind. That comes very handy. Okay, now here is an example of some code that creates an m by n list A of floats where all the elements are initialized to 0. Okay, we first start a one-dimensional list A, right? And then I goes from 0 all the way up to m minus 1. And for each such I, what we do is we construct a row, right? And a row is constructed as this list containing just the element 0 multiplied n times. All right. When you do that, you get a one-dimensional list that has n values which are all zeros. Okay, that's what this syntax does. So let me give you a concrete example. So let's say you take 0.0 and multiply it with 5. So this results in a list that has 5 elements which are all 0.0. Okay, so in general, if you have n columns, then this syntax has the effect of producing a list of n items where each is initialized to 0. Okay, and that list now here is appended to the A list. So you're simply appending a row to this list A, right? And once this code is done, what you have in memory is an m by n list A of floats with everything initialized to 0. Okay, so let's do a concrete example. Let's say m equals 2 and n equals 3. Well, how does this work? I is initially 0. Okay, and what we do here is we say row equals this thing times 3. So you're going to get this list here, 0.0, 0.0, 0.0, and that is appended to A. So A now is a one element list whose element is that. Okay, and then in the next iteration, I is going to take on the value 1, and we do again the same thing. We get a row that is this thing times 3, which gets me another list like that I append to A. So A is now a 2-element list whose elements are themselves lists containing 3 elements which are all zeros. So now notice that what we have at the end is a 2 by 3 list A, right? 2 by 3, 2 rows and 3 columns, where every element is initialized to 0.0. Okay, so that's that. So in case of a two-dimensional list, how do you get hold of a particular element? So let's say you want to get hold of the element at row I and column J. Well, the syntax, because of the way how two-dimensional lists are represented in memory, the syntax A at I simply refers to the ith row as a list. Okay, and once you have that list, you can get the element at the jth column of that list by saying A at I at J. Okay, so what we are saying here is that if you want to access the element at row I and column J, you simply use the syntax A at I at J, right? So A at I refers to the ith row, and then this guy refers to the jth column of that row. Okay. Here is some code that adds two n by n matrices A and B. Okay. And that shows how you access elements inside of a two-dimensional list. Right? So let's say A and B are two matrices of size n by n. How do you add the two? Well, we first create a new matrix called C to store the result. And that has exactly the same size as A and B, so it has n rows and n columns. So notice we are making use of the create 2D function that we talked about before from the stdarray API. So, and we are initializing every value to 0. Okay? So initially we are saying the result is simply an n by n matrix whose values are all 0. And then we calculate the sum of the two matrices using these nested for loops. I goes from 0 through n minus 1, and for each such I, j goes from 0 through n minus 1, and we're simply saying the ijth element in the result is the ijth element in the matrix A plus the ijth element in the matrix B. So it's simply component-wise addition. Okay? So let's look at a trace of this code on a simple example, simple input where A is the matrix 1, 2, 3, 4 and B is the matrix 2, 3, 4, 5. So how do you add these two guys? Well, here is how it's done. So I is initially 0, j is 0. So what is the ijth element in A? It is 1, this guy. What is the ijth element in B? Which it is 2, this fellow. You simply add them and you store it as the ijth element of C. So that's how you get 3 in the result. Okay, so C is now 3 at this point. So this is 0, this is 1, this is 0, this is 1. And then in the next iteration, I remains at 0, j is 1. So now you're looking at this element from A, and you're adding to that this particular element from B to get 5. Okay, so at I equals 0, j equals 1, you have 5. And then I becomes 1 and j goes to 0. So now you're looking at this particular element from A and this particular element from B. Add them, you get 7. So this is now 7. And finally, I is 1, j is 1. So you're looking at this element from A and that element from B. Add them together to get 9, and this is 9. Okay? So that's how you add two matrices together. Okay, so now let's look at a concrete example where we make use of a two-dimensional list. So this program is called self-avoid.py. What it does is it takes integers n and trials as command line arguments, and it performs trials number of what are called random self-avoiding walks, okay, in an n by n lattice. So an n by n lattice looks something like this. So in this case, n is 7. Okay, so this is a 7 by 7 lattice, right? So we perform a random self-avoiding walk. So what does that mean? It means in each trial we start with a lattice like this, and we start some individual somewhere smack in the middle. All right, so let's say there, and then this individual just walks at random by visiting a neighboring cell, a cell to the north, west, south, or east, picked at random. Right? And once the individual visits a particular cell, we remember the fact that we visited that cell. Okay, so we don't visit it again, right? And then we repeat the process. From there, again, the individual picks a random cell, north, east, west, or south, and goes to that cell and remembers the fact that she visited that cell, and so on. Now the question is, in that trial, by following this random process, is the individual going to escape? Meaning, is she going to reach the periphery, which is denoted in gray? Or is she going to be stuck, meaning not be able to get out? Okay, so there are two possibilities. in each experiment, you're in a dead-end scenario where you're stuck, or you're in an escape scenario where starting in the middle by following random walk, you end in the periphery. That's what we call an escape. All right, so it's either a dead end or an escape. Right? And for output, all that we want to do is print the percentage of dead ends encountered out of the trials experiments. So let's see how this is implemented. So we start by importing our usual modules, and then we get the two command line arguments, n and trials, as integers, and then we initialize a variable called dead ends to 0. So that's going to store the number of dead ends out of the trials number of experiments. And then we have a for loop that goes from 0 all the way up to trials minus 1. So the for loop is what is performing the trials number of experiments. And each experiment is the body of the for loop. Okay, so what do? We start with a lattice. So the lattice is represented by a matrix that has n rows and n columns. So it's an n-dimensional lattice, n by n lattice, where every element is initialized to false. So it's a Boolean array. And what does it mean to have every element initialized to false? It means that none of the cells have been visited so far. Right? That's what it means to say every element is false. And then we say x and y are n over 2 and n over 2. What does this mean? Well, this means that the individual starts at the middle of the lattice, smack in the middle. X is n divided by 2, y is n divided by 2. Right? Okay, so x is going to denote the rows and y is going to denote the columns. And the individual starts in the middle. And then we have this while loop that says if x is strictly greater than 0 and x is strictly less than n minus 1, and y is strictly greater than 0 and y is strictly less than n minus 1, do all this stuff. Well, what does this condition mean? So think about it carefully. What it means is that as long as the individual is not in the periphery, okay, so that's what this condition means. As long as the individual is not in any of these gray cells, do all this stuff. Okay? So in the first line, we say mark the fact that the individual is at cell XY. So the individual just got into XY. Remember the fact that she is now in XY. So we set A at XY to true. And then what we do is we check the cells to the north, south, west, and east, and if all of those are true, what does it mean? The cell to the north, cell to the south, cell to the west, cell to the east, if they're all true, it means that there is nowhere to go. All the neighbors have been visited, so it is a dead end. We increment dead ends by 1 and we break. And when we do a break, you're immediately out of the while loop and you perform the next experiment. Okay, you're out of the while loop, but you're still in the for loop, so you perform the next experiment. Okay, so that denotes a dead end. But what if it is not a dead end? Well, in that case, we get a random integer between 1 and 4. Okay? And then if that integer came out to be 1, then we check if the cell to the south has been visited or not. If it has not been visited, then we go to that cell. So we increment x by 1. Okay? But what if this expression is not true? Okay? So let's say R was not 1. Well, let's is it 2 then? Well, if it is 2, then we again check if the cell to the north has been visited or not. So R equals 1, we are interpreting it as south. So let me say S for south. R equals 2, we are interpreting it as north. So we're checking if R is 2, then if that cell has already been visited or not. Okay. If so, we decrement x by 1, meaning we go upwards by a cell. So x minus, or we do x equals x minus 1. But what if this was not true? And let's say R is 3. In that case, we check the cell to the east. Okay? So this denotes east. And see if that has been visited or not. If not, we go to that particular cell to the east by saying y plus equals 1. So x remains the same, but y is incremented by 1. And what if that expression is not true? Well, then it has to be this one. Okay, so one of these four expressions have to be true. R equals 1, 2, 3, or 4. So if R is 4, that is treated as west. We check if the cell to the west has been visited or not. If not, we go to the west. Okay, by keeping x fixed but decrementing y. Okay, so that's that. So, and it's clear that at some point we are going to be out of the while loop. We are going to be out of the while loop either by exhausting, meaning by reaching the periphery. Okay, because when you reach the periphery, it means you've escaped. Right? And in that case, you've also exhausted the loop. Or you can get out of the while loop prematurely via this break statement, which would mean a dead end. All right? Okay, and then once all the experiments are done, we simply report on the percentage dead ends, right? Which is simply 100 times dead ends divided by the total number of trials. Right? So that's that. And here's some input and output. We run it with n equals 5, a 5 by 5 lattice, 100 experiments, and here the program is saying that there was no dead end at all. So the individual was always able to escape. Then we increase the lattice size, and the trials is still 100. So here the program says there's about 31% dead ends. So 31%, 31 times out of the 100 trials, the individual got stuck. And then and so on and so on. And then here we are running it with n equals 80, 80 by 80 lattice, 1,000 experiments. And here what the program is saying is that about 98% of the time, meaning 998 times, the individual got stuck. So what we can conclude from here is that as the lattice gets bigger and bigger, the individual has very little chance of escaping the lattice, right? So most of the time the individual is going to encounter a dead end for big lattices. Okay, now a list. So we've talked about a two-dimensional list where every row has the same number of columns, but that need not be the case. A list can have rows with non-uniform length, meaning rows with different number of columns, and such a list is called a ragged list. So for example, this code here is able to write the contents of a ragged list. Okay, so let's say we are given a ragged list that has different number of columns in each row. So the first row might just have one element. The second row might have two elements. The third row might have three elements, and so on. So how do we print such a two-dimensional list? Well, this code will do it. So I goes from 0 all the way up to length of a minus 1. So I simply traces the rows. And then j goes from 0 all the way up to length of a at I. So notice that we don't say length of a of 0, but we say length of a of I, meaning we are asking for the length of the ith row, which is clearly different for different values of I. Okay, so when I is 0, this length of a of 0 is simply 1, so j is simply going to take on the value 0, and we look at this particular guy. Then when I is 1, length of a of 1 is 2, because this list has two elements, right? So the possible values for j are 0 and 1, so we're correctly going to print out these two guys. And then finally, when I is 2, which is for this list, length of a of 2 is going to be 3, because there are three elements here, and then j is going to take on the values 0, 1, and 2, so we correctly get these elements. Okay, so this code is capable of printing a ragged list, meaning a list that has different number of columns in each row. So if, for example, we have a list A, that is this two-dimensional list, which is ragged. Why is it ragged? Because the first row has one element, second row has two elements, third row has three elements, and so on, and then the fifth row has 5 elements. Okay, and so if this is your list, what would this for loop do? Well, it would print it in this fashion. Okay? This is the output that you would get when this for loop operates on this particular list. Okay? And so what is this list, by the way? Well, it represents Pascal's triangle of order 4. Okay? And it's very nicely printed out by this for loop. Right? Okay. Now, the notation that we used for one-dimensional and two-dimensional lists can also be extended to higher dimensional lists. Okay, so you can talk about a three-dimensional list, for example, and you can use the idea of lists of lists of lists to create a three-dimensional list A. And then once you have such a three-dimensional list A, you can refer to any particular element in there by saying A at I, at J, at K. Okay? So it's simply a generalization of the idea for one and two-dimensional lists. But in this course, we're going to restrict ourselves just to one and two-dimensional lists, right? But a three-dimensional list can be sort of visually thought of as being something like that, right? So you have these guys, this guys, okay? So I for rows, then let's say J for columns, and then K for the depth. Okay. So, but as I said, we're going to mostly work with one and two-dimensional lists in this course. All right, so we're done talking about lists. Now we need to talk about some other collections or data structures. So what is, so we're going to, the next data structure or collection we're going to talk about is a tuple. So tuple is an object of a built-in sequence type called tuple. Okay, and it simply consists of a number of values that are separated by commas. So the way you create a tuple in Python is by saying t equals the value separated by commas. So this is an example of a 3-element tuple. Okay? And then if you want to access the first element, you simply use the indexing syntax. So t square bracket 0 gets you the first element. T square brackets 2 is going to get you this element, and so on. Right? And then if you just say t in the Python shell, it simply prints out the tuple. So that's how you create a tuple and index a value from it. Now tuples can be nested. So here is an example of a tuple u whose first element is the tuple t from here. Right? And the second element is a tuple in itself. So if I now print u, it prints this. It's a tuple of tuples. Okay? And here, for example, if you do length of u, what is it going to be? Well, it's going to be 2 because it's a 2-element tuple. But what if you say length of u at 1? So u at 1 is talking about this particular tuple, and what is its length? That is 5. Okay? Now, keep in mind that tuples are immutable. I mean, they look a lot like lists and work a lot like lists, but they're different from lists in this fundamental way, that tuples are immutable, whereas lists are mutable. Okay? But tuples can contain mutable objects. Okay, and that is what is I want to illustrate now. So V is a tuple whose first element is a list 1, 2, 3, and the second element is the list 3, 2, 1. Okay, and if I print out V, this is what I get. Now, since tuples are immutable, I cannot say something like V at 0 equals 42. So I'm trying to change the 0th element from this list to 42. This is error. Not possible because tuples are immutable. But tuples can store mutable objects. So here the two elements that make up the tuple V are lists which are mutable. So I can say something like this. I can say V at 0, which refers to this list, and then it's, let's say, second element equals 42. So V at 0 is this guy, and V at 0 at 2 is talking about this guy. So I'm changing that to a 42, and that's allowed. Why? Because lists are mutable. Okay? So keep that in mind. Now this is how you create an empty tuple. that contains no elements. So in just put parenthesis. This is how you create a singleton tuple, or a tuple with exactly one element. Now here you need to remember the comma, because if you don't put this comma, singleton is just going to be the string hello, right? So if you want a single element tuple, remember this comma. So if you now ask for the length of empty, which is this guy, it returns 0. And if you ask the length of singleton, it's going to be 1. Okay? Now, there is something called sequence unpacking, which allows you to assign the values of a tuple to some variables. So if t is the tuple 7, 8, and 10, I can simply say x comma y comma z equals t, in which case x becomes 7, y equals 8, and z equals 10. So this implies that. Right? So that's what we call sequence unpacking. The next collection that we want to talk about is a set. And a set is an object of the built-in sequence type set, and it is an unordered collection with no duplicate elements. Okay, so a set doesn't contain duplicates and there is no ordering on it. So let's look at some examples. So here basket is a list containing all these strings, names of fruits, and fruit we set it to be a set that is made out of the elements of basket. Okay, so set, so this is this set type that we're talking about, and we simply give it basket, which is this list, and what set does is it turns this basket into a set. Okay, now if you look at fruit, notice what has happened. The ordering is kind of lost, and then all the there are no duplicates here. Okay, orange, which showed up 2 times here, only shows up once. Apple showed up a couple of times, but just once here, right? So that's what we're saying here. It's an unordered collection with no duplicate items. Now, we can check for membership in a set using the keyword in. So if you say string orange in fruit, it's going to return true because orange is contained in fruit. But if we say crabgrass in fruit, it returns false because that's not in this particular set. There are some set operations that you can perform on set objects. So if A and B are set built from this string and this string, what we can do is we can perform set operations on these two sets, right? But first of all, I mean, what is this set? Well, it is the set that are characters from here without duplicates. So it's going to be A, B, R, C, and D, right? Just those characters. And what is this set going to be? Well, it's the characters from this string without duplicates. A, L, C, Z, and N. And now you can perform set operations on these two guys. So if you say A minus B, what we get is a new set whose elements are in A but not in B. Okay, so if you do A minus B for these two guys, we simply get the new set R, D, and B, because these are the elements that are here but they are not in here. Okay, and then if you do A pipe B, you get a new set where the letters are in either A or B. So if you do A or B, we simply get a new set that contains letters that are here or here. That's what you see. And then if you do A ampersand B, it gives us a set that contains letters that are both in A and B. So for this particular example, the letters that are common to these sets are just A and C. That's what you see. Okay? And then finally, if you do A caret B, A hat B, what we get is a new set that contains letters are in A or B but not in both. Okay, meaning it doesn't include the common ones. So for this particular example, it's simply R, D, B, M, C, and L. Right? It doesn't include A and C, which were common to both. So given two sets, you can perform the standard set operations. Right? The next collection we want to discuss is a dictionary, which is an object of the built-in mapping type. So notice it's not a sequence type, but a mapping type called dict. Okay? And what is such a collection? Well, it's a collection, it's an unordered set of key value pairs. Okay? So it's a table-like structure where you have keys and you have values. Okay? And then the keys are unique. So the things that go here have to be unique. There shouldn't be any duplicate. So each key, let's say K1, is mapped to a value V1. K2 is mapped to V2 and so on. Okay? And here are some examples. So we first create a dictionary called telephone that contains two key value pairs. Okay? It contains the name Jack and it contains the phone number 4098. The second element is SAPE, and which is mapped to 4139. So that's this dictionary here. And then we add a new element to it, a new key value pair. So when you do this, we have a new entry that says Guido is 4127. Okay, that's what we get. And then we simply print tell out. So we get this guy, which is basically this dictionary, right? And then we add one more element, one more key value pair to it. So we say Irv is 4127. So notice that the values can be duplicates, but the keys cannot have duplicates, right? So it's that. And then again we print tell, we get this 5 element dictionary. And then finally we can use the in keyword to check for containment of keys. So you can check if Guido exists as a key in this dictionary and it comes back with true. Okay. Whereas if I say something like Swami in tell, that's going to give me false because Swami is not a key in this dictionary. Okay. So that's that. Now there is an alternate syntax for building a dictionary from a list. So you can have a list, which is what is shown here, that contains two tuples representing the key value pairs. So here we have a two tuple whose first element is the key, second element is a value, another tuple, first element key, second element value, and so on. And then if we give that list as an argument to dict, to the dict function, it builds a dictionary whose key value pairs are these three guys: SAPE 4139, Guido 4127, and Jack 4098. So it's just an alternate syntax for creating a dictionary from a list. Now, comprehensions are constructs that provide a concise way to create collections. So let's first start with list comprehensions. So let's say you want to build a list called squares that contains the squares of the elements from the list 1 through or 0 through 9, right? So what we want is a list that looks like that: 0, 1, 4, 9, and so on, all the way up to 81. Okay? We want the squares of the numbers from 0 through 9. So we can certainly set it up using for loop and whatnot. Start with an empty list, do a for loop, and append square of I to that list, and we'll have this. But that's 4 lines of code. We can do that very nicely using a single line, right? And here's the syntax. So we say squares is a one-dimensional list, which is denoted by square brackets here, containing elements x square, where x takes on the values from 0 through 9. So that's how you want to read it. So for each value of x from 0 through 9, simply add x squared to the list. So once this is done, we have the list that we want. Right? That's what you see here. Okay, here's another example. So we are building a list, okay, that contains elements xy. So the elements of this list are two tuples. Okay, and x takes on values from this list 1, 2, 3, and y takes on values from this list 3, 1, 4, and we include xy in the list only if x is different from y. All right. So let's see how this works. So initially x is 1 and y is 3. All right. Is x different from y? Yes, it is. So 1, 3 is included in the resulting list. And then x remains at 1 and y becomes the second element 1. But now x and y are the same, so that's not included in the list, okay? Because we want to include them only when x is different from y. And then x remains at 1, y is 4, 1 and 4 are different, so we include that. And then what happens is y is exhausted, so x now becomes 2, and y is 3. 2 and 3 are different, so we include it. And then y becomes 1, 2 and 1 are different, we include it. And then y becomes 4, 2 and 4 are different, we include it. Right? And then y is exhausted again, x becomes 3. 3 and 3 are the same, we don't include. And then y becomes 1, 3 and 1 are different, we include. Y becomes 4, 3 and 4 are different, so we include. Right? So that's how that comprehension works. Notice, I mean, here again, you can certainly use for loops to build this list, but it's much more compact doing it using comprehensions. Here is another example of a nested comprehension, right? So let's say we are given a matrix which is shown here. So this matrix is basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And what we want to do is transpose this, okay? So we want to end up with 1, 5, 9, 2, 6, 10, 3, 7, 11, and 4, 8, and 12. Okay, so this matrix had 3 rows and 4 columns, and this matrix has 4 rows and 3 columns, and the elements are all transposed. Okay, so how do we do that? Here again, you can use a for loop to achieve this, but it's much more compact using doing it using a comprehension, and that's what is done here. So we have a comprehension. So we are saying we want a list that contains another list within, okay, which is what is shown by this guy here, whose elements are row at I. Okay? So how do we parse this? So initially I takes on the value 0. Okay? And for each such I, row goes through all the rows in the matrix. So when I is 0, row is initially the first row. So we simply say row at 0, which is this element. So we include that in the list. So that's how we get this guy here. Right? And then what happens is I remains at 0, but now row is the second row. What is row at 0 then? Well, it is 5, and we include that in our result. So that's how you get that 5. And then I remains at 0, but row now becomes the third row. So row at 0 is 9. That's how we get that. But now notice that the inner loop is done. So I becomes 1. And now row goes back to the first row. So row at 1 is 2. That's how we get that. And then row becomes the second row. So row at 1 is 6. We get that. And then row becomes the third row. So row at 1 is now 10. So we get that, and so on and so on and so on. So as you can see, this comprehension correctly gives us the transpose of the given matrix, which is what is shown here. Right? You can also perform set comprehensions. So here, for example, we are building a set called A that contains the elements X, where X takes on values which are characters from the string. So this is familiar syntax. So X is simply enumerating the characters of the string, right? And then we include X in the set only if it is not from the string ABC. So we look at a character from here. If it is not in this particular string, we include it. Okay. So how does this work? So we go through A, but it is in the string, we don't include it. Then we look at B. So X is B. It is in this, we don't include. Then X becomes R. It's not in here, so we include it. That's how you get R in the output set. Right? And then X becomes A. It's in here, we don't include. C, don't include. A, don't include. D, not in here, so we include. So that's how you get D there. And then A, we don't include. B, we don't include. R, we don't. R, we should include, but then we are building a set, so there's no duplicates, right? So that's why this R doesn't show up the second time. And then finally A, we don't include. Okay, so that's a set comprehension. And then we can also perform dictionary we can also have dictionary comprehensions. So let's say we want to build a dictionary whose key value pairs are 2, 4, 4, 16, and 6, 36. Okay? So how do we do this? Well, this comprehension does it. So we are creating a dictionary whose keys are x and values are x squared, where x takes on the values 0, 2, 4, and 6. Notice that this is a tuple. Okay? It turns out that even tuples are iterable, so you can put them here in a for loop. Okay? So x is initially 2, so the key value pair 2 and 4 is in the dictionary. X becomes 4, the key value pair 4 and 16 is in the dictionary. Then x becomes 6, the key value pair 6 and 36 are in the dictionary. Okay? So nice little example of a dictionary comprehension. Okay, the last topic then is to look at some advanced looping techniques. All right? Now, when you're looping through a sequence, the position index and the corresponding value can be retrieved at the same time using what is called the enumerate built-in function. So far we have talked about iterating over a list using either index or value, right? But what if you want access to both? Well, you use the enumerate function. So here is an example. So we say for I comma v, I for index and v for value, these are just variable names. You can call them whatever you want, but I is a good name for an index and v is a good name for a value. So we say for I be in enumerate, and we give the list as an argument to enumerate, right? And the list simply has 3 strings, tick, tack, and toe. And then in each iteration, what we do is we print the index concatenated with the value. Right? So how does this work? In the first iteration, I is the index of the first element, which is 0. The value is tick, so we end up printing 0, tick. In the next iteration, I is the index 1. The corresponding value v is tack, so we end up printing 1, tack. And the last iteration, I is the index 2, and the value is toe. So v is toe, so we print 2 and toe. Okay. So if you want to have access to both index and value at the same time, you want to use the enumerate function. Now, if you want to loop over 2 or more sequences at the same time, you can pair up the entries with what is called the zip built-in function. So far we've been iterating over just one individual list, but you can iterate over multiple lists at the same time, okay, using the zip built-in function. But and here is an example of that. So questions is a list containing those elements, answers is a list that is containing those elements, and then we can say something like for q comma a in zip of questions and answers, okay, write this string to the output. So what is your q, or what is your question, and it is a for answer. Right? So in the first iteration, q is going to be name, so this is going to be q, and a is going to be Lancelot. So we write the string, what is your name, it is Lancelot. Right? So that's that. And then in the next iteration, q is going to be quest, a is going to be the Holy Grail. So we end up writing, what is your quest, it is the Holy Grail. And then in the last iteration, q is going to be favorite color, a is going to be blue, and we end up writing, what is your favorite color, it is blue. All right? So you can use the zip function to simultaneously enumerate sequences. If you want to loop over a sequence in the reverse order, then you can first specify the sequence in the forward direction and simply call the reversed function. So here is an example of that. So you say range 1, 10, 2, which simply gives you the list 1, 2, and so on, all the way up to 9. Oh, sorry, actually that's not correct. So this gives you the list 1, 3, 5, 7, and 9. So that's the list you get from range. And then if you say reversed of that list and enumerate that, then you get things in the reverse order. So I now, so reverse then of that is going to be the reverse of this guy, 9, 7, 5, 3, and 1. So now I takes on the value 9 first, which gets printed, and then I takes on the value 7, which is printed next, and so on, all the way down to 1. Okay, so you can specify your sequence in the forward direction and simply reverse it using reversed and enumerate that, in which case the elements are going to come out in the reversed order. And then if you want to loop over a sequence in a sorted order, you can use the sorted built-in function, okay, which simply returns a new sorted list without leaving the original list unaltered, without altering the original list. Okay. So let's say basket is a list that contains these elements in it. So what we can do is first turn it into a set, all right, which will remove all the duplicates. So this, for example, will be gone, and orange would be gone. And then what we do is we call sorted on that set, okay, which is basically all these guys without duplicates. And then sorted returns a new list, which is this list sorted, or this set sorted. Okay? And then you enumerate that sorted set and print the elements out. That's why you see all these elements, 4 of them, 1, 2, 3, and 4, printed in sorted order. Okay, so it's the sorted that puts this set in sorted order, and when you simply go through its elements and print them out, they come out in sorted order. Okay? But it's important to realize that sorted does not modify the input list. It returns a new list that is the sorted copy of the original one, but the original is left unaltered. Okay? All right, so that concludes this lecture on collections. Thanks for your time.